Okay, let's work on this problem. Again, we're going to write equations for slope and displacement for the beam. And as we discussed just a minute ago, what makes this problem a little different is the fact that I can't write a single moment expression for the entire beam. You can see because of this load P, I'm going to have a moment expression for the first half of the beam and a different one for the second half. The first thing I want to do is find my reactions. I don't think I need to write a moment equation for that. I think you can see that the reactions are just going to be P over 2. So I'll shortcut that a little bit. When I cut it somewhere between 0 and L over 2, and I want to work either the left side or the right side, which one do you think is going to be a little easier to deal with? Yeah, I think the left side is going to be easier. So I'm going to draw a free body diagram of that left side. Has a distance x, and I have the reaction P over 2, and I have my internal moment that I'm trying to find. So this is my positive bending moment. So now if I sum moments about the cut and assume right-hand rule for my sign convention, it shouldn't be too hard to find what that internal moment is. So what is the sign of this moment with this assumption for sign? It's positive. What about the moment about the cut due to this P over 2 function? Negative. So the force is P over 2 and the distance is x. So I guess you can see that this moment, I'll call it moment 1 in the first section, is simply just Px over 2. Now remember, this is only going to be valid over the first half. Because if I plug in x equal L here, what do I get? I get PL over 2, but at x equal L, what's the moment? 0. So it doesn't work. It does work on the first half of the beam. When I plug in x equals 0, what do I get? 0. So that matches the one place I know there. Now I want to come over this second area and make a cut. Do you want to work the left side of that one or the right side? Right. Yeah, I think the right side is going to be easier. And that distance is going to be L minus x, and we're going to look to the right. So if I draw that free body diagram, so at this distance x, the length of the beam would be L minus x. This is positive bending moment at the cut. And I forgot my reaction, which is P over 2. Is that pretty much it? I think that's all that's there. So we'll do the same thing as we did before. We'll sum the moments at the cut. Again, I'll assume right-hand rule for the sign convention. Now this positive bending moment with this static sign convention is negative. And the moment of this force P2 about the cut is positive. So it would be P over 2, and the length would be L minus x. So in this case, the moment in the second section is going to be P over 2 times L minus x. That should be good from L over 2 to L. Now, does it work? Well, just like up here where I checked that the moment at x equals 0 was in fact 0, that was the one thing I did know there. Here I'm going to check that the moment at x equal L should be 0. Is that true? Yep. So it matches the two ends. One other thing I can check before I go on is that the moment produced from the first equation at x equal L over 2 should match the moment produced from the second equation at the same point. They have the same value. Is that true? When you plug in L over 2 here, you get PL over 4. You plug in L here, you get PL over 4. So they do match. Is that so far so good? Any questions about that? If you're not happy with that, you could always draw the shear moment diagram and see that the moment diagram does look exactly like these two values. So what do I have to do next? I got to integrate these guys. So that means I'm going to get, since I have a moment expression from 0 to L over 2, I'm going to get a slope expression that's good from 0 to L over 2. And a displacement expression that's good for that range. And then another set here. Let's look ahead a bit. As I do my integration, my double integration here to convert this moment to a displacement, how many integration constants will I generate? 2. And when I do this section and double integrate that, I'll get 2 more. And then with 4. What 4 conditions do I have? Well, I know the displacement at A and the displacement at B are 0. What else do I know?
Displacement is max at L over 2.
Does that tell you what the displacement is? You do know that probably because of this loading, that the slope at the center should be 0. If I move this load just a little bit left or right, is that true anymore? No. So a safer way would be to do what at where the two equations meet, just like I matched the moment. What else should match? The slope and displacement. So I'd have one condition, displacement at A, second condition, displacement at B, third condition, matching slope at the center, fourth condition, matching displacement at the center. 4 equations, 4 unknowns. This is where you can go, ouch. This is a great method. It works great, but now the mathematics becomes a little more challenging. So I'm going to flip to a new page to write the equation, so it won't jam it up as bad. So let's start with the first region. So the slope in the first region is going to be the integral of the moment from the first region divided by EI. You may not remember, but we had our first moment expression was px over 2. So I'll pull the p and the 2 out. So I'll have p over 2 EI, and I'm left with just the integral of x dx.
First moment over EI?
None of the moments are over EI. When you integrate the moment, you divide it by EI to get the slope.
Yeah, but that's not moment I.
No, that's the moment in section 1.
Yeah.
That's Roman numeral 1. That's not that I. Yeah, symbols, huh? So that ends up being P over 2 EI times x squared over 2 plus our first integration constant. Now for this particular problem, I could go right now at L over 2 and make sure that at L over 2 the slope is 0 for this problem only. Right? Because we know since the load is right in the middle and symmetric, the maximum displacement will occur at L over 2. So the slope is 0 at L over 2. Like I said, if this force moves a little bit off center in either direction, that's not true. So I'm just going to hold on to it right now. My objective here is not to show you how to solve this problem, but how to solve one of these problems in general. Okay, so now the displacement in the first section is the integral of the slope. So I just integrate that. And again, you can see I've got P over 2EI. And this becomes x cubed over 6 plus C1x plus C2. So really now I have two equations in two unknowns. But right now I only have really one condition that I'm sure of. The displacement at A in that zone is 0. So let's go ahead and now integrate the second set of equations. So this is the slope in section 2 is the moment in section 2 divided by EI. Again, a P over 2 can come out. So I'll have a P over 2EI on the outside, and then I'll have the integral of L minus X. Which is P over 2EI, again, the constant. And then inside I'll have Lx minus x squared over 2. And then I'll generate a third integration constant. So now the displacement is the integral of the slope. So just integrate that. So again, my constant is still P over 2EI. And internally this becomes L x squared over 2 minus L cubed over 6 C3x, and then a new integration constant C4. So this becomes my third and fourth equation. What are my four conditions? Well, I know that the displacement at x equals 0 is 0. I know the displacement at x equal L is 0. Those are the two that we know for sure from our conditions. Now for this particular problem, I know that the slope at 1 and the slope at 2 at L over 2 are 0. Again, that's only for this problem. In general, that won't work. But what will work every time is that the slope from the first equation at the point they meet, which happens to be L over 2, has to match the slope from the second at the same point. And also the displacements have to match. So we can't have discontinuities in the displacement or the slope. So there's your four conditions for your four equations. And applied that way, you can't solve these one at a time. They have to be solved simultaneously. And one thing I don't like about the author's approach to this is he just says, solving the equations gives this. When that's really a little bit of a challenge to solve those equations. Especially the way I've done them here, we're working these symbolically. They're not numbers. You can't just plug it into your calculator and get a numerical response. It's a little bit of a trick. Now, is it really super hard? No. With the resources we have today, it's a trivial problem to put into a piece of software like MATLAB or something like that. It would solve them without much trouble. But for what we're trying to accomplish in class, in the exam, this is where you would stop. If I gave you a problem like this, all I'd like to see is that you develop the appropriate equations and tell me what you would do to solve those equations. And that would be good enough for me. Okay? In our small 15-minute window time in the exam, that's all they really have. I mean, we've been working on this for about 15 minutes. That's pretty clever. Any questions about that? I just wanted to remind you again that the advantage of this method is that it works great. You can apply it to just about any beam you want to know. But as the number of moment equations increases, you can see the level of complexity for the solution increases. Again, given all the resources in the world, could you solve this problem? Of course you could. Given a 15-minute window with your pencil and a piece of paper, of course you can. But you can set it up. And that shows me that you understand the problem, and given the time, you can solve it. That's my view of it. So any other questions before we stop? Okay.
That wouldn't work if the L's were different, right? Like if the section 1 and section 2 were different lengths.
No, this would be exactly the same regardless of what this was.
Okay. So if you had like half L and 3/4 L.
Everything would the moment equations might be different in their form, but these would be the same, except that whatever point they share, you would match them. Now, in this particular problem, as I mentioned before, we know some things. Like, I can go get C1 right off the bat because I know at L over 2, the slope should be 0. So I can get C1. I can slide down here, and at L over 2, I can get C3. And then, since I know C1, I can find C2 by matching this one. And since I know C3, I can find C4 by matching that. So there's a very shortcut solution to this problem if these lengths are equal. But only this problem. A general problem that looks like this, where these are unequal, that solution process won't work because you don't know where the slope is 0. In this problem, you have some insight that the slope is 0. You guys are looking at me like I'm crazy. Remember, the displacement looks like that, so we know that right at that point there, what's true? That's maximum displacement, so the slope is 0. That's only this problem, not in general. The slope is not 0 at the center of the beam for any beam. Okay? But this relationships are true anywhere you apply it. So I think this is the more reliable approach.
Is it always 0 underneath the load?
No.
No.
An easy example to see that would be the same beam. I think Mr. Griffin mentioned it earlier too. I have the same beam, and let's shift the load off to one side. Okay. Is it going to be 0 slope under the load? No. Somewhere there'll be a 0 slope, but I don't know where it's going to be off the top of my head. And you probably don't either. If you do, then you have Rain Man skills, and you need to go to graduate school immediately and start making some improvement in our world. If you can see that. There's an autistic guy who sees numbers as colors, and he just colors appear to him, and when he sees the colors and translates it, it's the correct answer to a problem. So he doesn't even know how he does it. He just sees it. It just happens. If you're one of those people, please step forward so we can abuse you. Put you to work on something important.